Hello everybody, my name's Tom Scragg. I'm a researcher associated with the observatory here at Catunzi. My role has been to develop a pulsar timing system as part of my PhD program for the observatory. The equipment's on site, still being commissioned, and is located in the equipment room the other side of the control space in the building you're in currently. I'm going to talk about pulsar timing and back-end systems, that the computing elements, the electronics that enable us to do pulsar timing. A quick recap. What are pulsars? Well, as we covered in an earlier lecture, they are not pulsating stars. Instead, it's a steady beam of radiation from the magnetic pole of a neutron star that flashes across our line of sight as the neutron star rotates around a rotation axis that's not aligned with the magnetic poles. Neutron stars themselves are formed from the remnants of a supernova explosion and mass about 1.5 to 2.5 times the mass of our sun, and anything from 10 to 20 kilometers in diameter. The physics we can do with pulsars, what makes them so interesting, is that they interact with their environment. So by looking at the time of arrival of a pulse signal at different frequencies, we can glean information about the interstellar medium along the line of sight. We talked about dispersion measure again in the previous talk on pulsars. If we look at the pulse profile, it can give us information on the structure present in the emitting regions in the magnetic poles of the pulsar. Pulsar timing itself, looking at how the rotation speed of the pulsar changes, gives us a lot of information as to how the body is interacting with its environment. Pulsars slow down because of that interaction. We can measure that slowdown. We have ORATs and nulling emission modes where the pulsar continues to rotate, but we don't actually see the emission for a period. And we'll have an illustration of that a little bit later as well. And we can detect glitches, that's speeding up of the rotation period based on an interaction between the surface and the interior of the neutron star. Pulsars in binary systems give us a lot of information on gravitation and interaction between the stars themselves. So what is pulsar timing? We get a periodic signal from a pulsar. We build a timing model based on the information that we received so that we can predict the behavior of the pulsar into the future. We then continue to monitor the pulse time of arrivals from the pulsars and compare it with the predictions of the model and continually refine the model. So this is how we know that pulsars slow down over time, for example. If we have a simple rotation model that says it occurs every second ad infinitum, we find it drifts. We find the pulses are arriving at a slower rate in the future than we predicted. That again gives us information on how the pulsar is behaving and interacting with its environment. We want a great deal of accuracy in our pulsar timing. The more accurate the figures are, the more accurate the model, the better we can actually understand the behaviors and what's actually happening with the pulsar. So if we measure a simple from one rotation to the next with the figures that we've got there, 1 second period, 10% duty cycle, and we can measure the accuracy of the peak of the pulsar, the peak of the signal rather, to 10%, then we've got an accuracy of maybe 100 milliseconds in the rotation period. But if we measure that over 1 million pulses, we can reduce that error by 10 to the 6. The most accurate timed pulsar we have at the moment, PSR J1737 plus 0747, the very rapidly spinning millisecond pulsar with a period of about 4.5 milliseconds, we've actually measured down to 10 to the -8 of a nanosecond by observing it for a very long time and developing very detailed models based on its behavior. Okay, so Pulsar Backend Systems. There's 3 types of system at the observatory. There's the radio receiver itself, there's a signal digitizer or analog to digital converter, and then there's the Pulsar timing system. There are lots of other systems, obviously, but these are the 3 we're interested in. And we're only going to look in detail at the Pulsar timing system. The original Pulsar timers were analog devices. Pulsars were discovered using a pen chart recorder, looking at a very bright pulsar signal, of which we've got an example on the next slide. So we've got the chart recorder. This is the notes from the original detection of the first pulsar by Jocelyn Bell and Anthony Hewis in 1967, published a paper the following year. Chart recorders are good, they're simple, they're cheap. You have to go through an awful lot of paper because the sensitivity is very limited. You can't add signals together. So you're reliant on the pulsar being bright enough to observe on its own and being visible above the noise level in the receiver and the environment that you're working in. The next analog system is a filter bank. We've talked about dispersion before and the fact that pulsar signals can be quite faint. Dispersion means that the signal is spread over quite a number of rotation periods or even a number of seconds. So it's very low, very faint. If we can somehow determine the dispersion and de-disperse the signal, we combine the signals in different frequency channels together to get a brighter pulse that we can detect with less sensitive equipment. The problem with the analog system is we can correct each frequency channel, but we don't correct the signal within the frequency channel. So you can see the slope on the blue lines on the figure on the right-hand side actually still gives us some smearing of the pulse, but we do get we do gain information based on that. Next development was for digital filter banks rather than analog ones, where you're tuning the delay times based individually for each frequency channel based on the dispersion measure for the pulsar. Well, at least with a digital filter bank, you can arrange to tune that delay based on an overall value electronically rather than mechanically. They're very specific pieces of equipment developed for this application. The technology to do it's been around for a while, but it is a limited resource in terms of the people that can design ASICs and FPGAs. If you change your algorithm or you want to extend to pulsars you've discovered further away, for example, effectively you have to build a new filter bank system, because the ASICs and the FPGAs are the heart of the system. Next development came when we got general purpose computers with sufficient power to process the mathematics associated with pulsar timing. They have many advantages. They're flexible, they're cheaper because we can buy them off the shelf. Lots of people know how to program, interested in programming. We can change the hardware, we can change the software, and still keep the basic system as it is. In order to get the processing power we need, what people built were clusters, where the individual frequency channels, the signal from the pulsar was split into individual frequency channels and then routed to a processing server, processing node. And that computer just looked after its own part of the signal. They were then combined later on to give us the overall improvements from bandwidth and signal to noise. Clusters of identical nodes were called Beowulf clusters, and that enabled us to process data at much higher rates. And this is just a very outline schematic of the current current cluster at Jodrell Bank, attached to the back of the Lovell telescope, called Jumper. One of the advantages of the general purpose computer is we can do coherent dispersion and folding the data in real time. That means we don't have to have huge amounts of storage and a system that processes the information offline after the observation is complete. We can actually do it as we're observing. There are limitations on the design of CPU-based pulsar timing systems. And this is a quick illustration of a Core Duo CPU from Intel, where we've got two CPUs. Each one has 4 cores, and they share a certain amount of hardware and infrastructure within the server together. So the more data we throw at the system, the faster it goes, until we reach a point where each CPU can no longer work independently, and you get contention for memory and eventually contention for access to the bus to get the data from the RAM, indicated by the grey lines on the picture on the left, and you see the throughput collapse. So we go to a certain speed, but if we try and go beyond that, it just stops working effectively. It doesn't degrade slowly, it can drop off quite steeply. The software environment you're working in as well is key to your performance. So let's look at some of the challenges for the pulsar timing system. So we talked about signal to noise. Some of the pulsars are so faint, you can't detect them with a single rotation. You have to add together a very long duration observation. Second thing is those individual pulses from a pulsar are not all the same shape. You can see the pattern on the right-hand side of the screen. I'm showing how each individual pulse is completely different one to the next. And the blank patches that you can see here and here is the nulling that we talked about earlier, where the emission from the pulsar either switches off completely or becomes so faint we can't detect it with our system. What we do see is the overall pulse profile for a particular pulsar is quite constant. Different for different pulsars, but for a individual pulsar, it's kind of a signature. The figure on the left, again, just illustrates some of the variability in the actual peaks that we receive from a pulsar for every rotation. It's only when you add a lot of these together that you get this pulse profile that we see. One of the things we want to do is coherently de-disperse the signal. That is correct for the problems within the delays, beg your pardon, within each frequency channel, so that we get the maximum signal to noise ratio. We can do that in software if we've got a processor that's fast enough. And the technology came from what's called a chirp filter used in military radars originally. It gives you a better signal to noise, but you need a lot of processing power to underdo this. If you do it in real time, like we mentioned earlier, you don't have to store the original data and then process it later. That's really just putting the problem off, because at some stage or other, you've got to process this information to make it usable. As an illustration, on the left-hand side, we've got a incoherently de-dispersed profile for the Pulsar 1737 plus 21. And on the right-hand side is the coherently de-dispersed pulse profile, based on correcting the signal within the frequency channel as well as between frequency channels. You can see there's a lot more structure, a lot more information available from the plot on the right-hand side. One of the final challenges that we've got to look at for pulsar timing systems is the increasing data rates. We have an exercise after this lecture, but it will talk about bandwidth, digitization of data, how much information do we have available. But for example, for the Lovell telescope, we have an overall bandwidth of 512 megahertz. We sample those at a very high frequency rate, corresponding to the observing frequency on the Lovell. And that generates 1 gigabyte of data per second, just for a single polarization. For context, a Blu-ray DVD, high resolution, high definition DVD, 3-hour movie is about 3 to 4 megabytes. So we're generating that every 4 seconds. We've also got to store that data for a time and process it because of correcting for de-dispersion. So we could have many seconds of data that we have to process. Before I move on to talk about the next generation of pulsar timing systems, which is the hybrid cluster, the device that's in the equipment room at Katunsi. This is just a graph showing how processing power, processing capability has improved over the years. We'll stop at this point for any questions.